In this video, we're going to have a look at how we can solve equations that involve trigonometric functions that have undergone a horizontal translation. So notice in this particular example here that we're about to solve is we've got a horizontal translation of a factor of pi on 3. Now to solve these equations, it's very similar to the previous ones, except we take some slightly different steps along the way, or slightly different choices along the way, purely for speed. So in this particular equation, I'm going to solve it like I would any other, and the first thing I'm going to start with is this vertical translation. So I'm going to take root 3 from both sides, and that will leave us with negative x plus pi over 3, and then half sine, and then I'm going to divide both sides by 2 as such. Now the next step I want to do is notice that there's a negative in here. If you recall back to the trig identity of negative sine x is equal to sine negative x, what we're going to do is we're going to use this here on this here to make our equation a little bit easier to work with. So we're going to get this on the right hand side, and then on the left hand side we're going to see negative half x minus pi over 3 as such. Then I'm going to apply this identity above, and we'll get negative sine a half x minus pi on 3, and that will be negative root 3 on 2, and then both of these, they come positive because we can multiply both sides by negative 1. And then the next step is we're going to go let theta equal a half times x minus pi on 3, and then this will remove the translation and the dilation just for now. So what we're left with is a form that's much easier to work with, so I'm sure we all feel much comfortable solving this particular problem here. Now using the unit circle, as always, to get our next solutions, or find all of our solutions, quickly draw it up just for good practice, and put our unit circle in. Perfect. What we're going to expect is, using the mnemonic of all stations to central, we're going to expect, because this is positive here, we're going to expect a solution in quadrant 1 and then a solution in quadrant 2. So quadrant 1, it's just going to be theta, and then to explain this interior angle here for quadrant 2, it's going to be pi minus theta. So the first solution for this particular problem is going to be theta equals the inverse sine function of root 3 over 2. And we all know from the exact values, or simply by memorizing the exact values for at least the first quadrant, the first solution is going to be pi over 3 radians. And then our, actually I should mark that as first solution, just so the marker knows that we know what we're doing. Then our second one is going to be theta, but rather pi on 3 equals pi minus theta, and we're after theta as always, so theta is going to be pi minus pi on 3, and that will simply equal out to 2 pi over 3 radians, and this will be our second solution. Now in the past, when I've done these sort of problems, I've always gone up and I've grabbed the domain and I've changed it in terms of, so in this case it's x, but down here we're working in terms of theta. So in the past what I'd been doing is I'd been changing the domain here to be in terms of theta, but for this particular question I'm not going to do it. And the reason I'm not going to do it for this question is because we've got this horizontal translation here. So what this horizontal translation will do is it will make us have to do a number of different calculations to change this domain around, get all the solutions, verify we're in the correct area, or all our solutions are valid, and then to go back. It's actually a bit quicker to sort of ignore the domain for now, calculate all of the solutions in terms of theta, go back to being in terms of x, and then verify whether you've got all of your solutions or not once you're back in x. If you don't have them, then you can go back and find more. Or if you've exceeded the constraints of the domain, you can clip them off, but it's purely a time choice here of ignoring the domain for now. Of course, you can do it with the previous questions as well, but again, the time factor is not as critical as when you're doing these sort of questions here. So moving on and ignoring the domain just for now, what we're going to write is theta equals pi on 3 plus 2k pi. And then the second solution is 2 pi on 3 plus 2k pi. And we have to explain what k is. So we're going to say where k is a positive integer between 0 and 1. Now the next question might be, well, how do I know it's between 0 and 1? And again, that's simply by looking at the original question posed here and then factored down to, let's say, just before we started working in terms of theta. So I'll highlight it in green. So where is it? This guy here and here, and the original domain here. So going across, we ask ourselves, what's the period going to be for this particular function? And the period's going to be 2 pi divided by n. N in this case is a half, so what we're going to get is a period of 4 pi. And then the next question is, well, how many cycles are we expecting? And it's going to be 8 pi minus 0 all over 4 pi. And that's going to be reduced down to, we're going to get 2 cycles, and k is equal to the number of cycles minus 1. So 2 minus 1 is simply 1. So, whoops, I should say maximum value of k. So that's where our 0 and 1 come from here. Again, we don't have to explain this bit. It's sort of assumed that you can work it out based on the domain up here. Now moving onwards, what we can say is, whoops, getting a thinner pen. Rather than going and working out all of these solutions, so doing this, we're going to get a half x minus pi on 3 is equal to pi on 3 plus 2k pi, and then 2 pi on 3 plus 2k pi, and then we need to have a common denominator here, so we're going to get 3, that's going to be pi on 6k pi, then 3 again, 2 pi plus 6k pi, and then multiplying both sides by 2 to get rid of the half. On the left hand side, we're going to get x equals pi on 3 then this will become, do it over 2 lines, 2 pi plus 12k pi, and then similarly 4 pi plus 12k pi. And then we have to deal with this phase here. So I'm going to add pi on 3 to both sides of the equation. So what that will evaluate at to will be 2 pi plus 12k pi all over 3 plus pi over 3. And then we're going to have 4 pi plus 12k pi, 3 plus pi over 3. And continuing onwards, this will evaluate to be, luckily these are in a common denominator, so there's no work in between. We can simply say 3 pi plus 12k pi all over 3, and then we can say not 4 pi but 5 pi plus 12k pi all over 3, and then these are nice numbers here, so what I'll do is I'll get rid of the denominator and divide everything through, so it will be pi plus 4k pi, and then I can't do anything about this 5 pi, so what I'll do is I'll just leave that as is for now. And remembering that k is equal to 0 all the way up to 1, so all the integers between 0 and 1, so we can say all of our solutions are going to be pi plus 4k pi, where k is 0, it's going to be simply pi radians, and then this one's going to be 5 pi plus 0, so that will be 5 pi on 3 radians. Then the one after that is going to be pi plus 4 pi, so that will be 5 pi radians. And then the final solution is going to be 5 pi plus 12 pi over 3, so 5 plus 12 is 17. It's a lovely prime number, so that's not going to get factorized down. So 17 pi on 3, and that would be our solutions for x. Now if we do it in a different color, if we go back and we compare it to the domain of 0 to 8 pi, what we need to make sure is that our first solution is above 0 and our final solutions are below 8 pi. So 15 divided by 3 is going to be 5. So we're well and truly within this 8 pi limit. So we can say with quite high amounts of certainty that we've managed to get all of the solutions to this, all of the solutions to this particular problem right there. So this would be an example of how we would solve could solve equations that contain trigonometric functions that have undergone the horizontal dilation here, denoted by this plus pi on 3.